trip, or?
Yeah.
Yeah.
We'll be more comfortable.
You will be, although you'll be cold in the next week or two. Well, Andy's always late, so he's probably coming. Dave, I don't know what his story is. We'll see. Okay, we're ready to go. Okay, today we continue our discussion of material functions. Everybody's got their exam back, so if you have any questions, I don't feel I have to go over it, but I'd be happy to answer individual questions. The solution's on the web. So we're in good shape, I think. I will comment maybe that that I hope that you find yourself very comfortable with this type of information that was asked on the test. Now, it may be the case that maybe you answered the question, you got it right, and that's all for the good, but you don't feel that comfortable. So if you feel that way, please come and see me, and we'll work on it a little bit together to try to make sure that you're really comfortable with that material, because when we move on to non-Newtonian constitutive equations, we're going to push the envelope back further. So we need to know this material and understand how it all goes together. So for now, we're going to move forward on material functions. Let me review the general topic, beginning with these slides. We're talking about material functions, which we're going to look at in this quadrant down here. We're going to compare measured with predicted and use it for developing constitutive models. And we've already done that. We've already looked at data from the literature, and I'll be reviewing some as I review these slides. We've predicted using the only constitutive equation we have, which is the Newtonian. Plus, in fact, we've done a prediction with a fake constitutive equation that we came up with that we thought might be a nice improvement. So we're already doing these two things, measuring and predicting constitutive equations. So all of our material functions start off with a choice of the flow, choice of the details, and then functions that are defined based on the stresses that are produced by this flow. Now we know that these flows only produce this limited number of stresses because of all the things we talked about in previous weeks about flow symmetry and symmetry of the stress tensor and things like that. All of our material functions will have a slide like this, which defines the velocity field that must be imposed. You either impose it on the constitutive equation by plugging it into the constitutive equation, or you impose it on the fluid by making a rheometer that does this flow. So we haven't talked too much about the specifics of rheometers that do our two flows, but we take it as a given that that has to be done. Our last week of the semester, we'll talk about what devices you need to use in order to get this flow to appear. But you can trust me for now that there are such devices. The stresses in a shear flow are shear and first normal, and here are the material functions defined for steady shear flow. And we did a prediction for Newtonian fluids and found that it predicts that there is no first normal stress coefficient and a constant viscosity. And then we compared it with the literature, and we saw that viscosity is in general not constant, and psi1 is in general not zero. This is polybutadiene. These are polybutadienes of different weights. Again, non-constant viscosity, non-zero psi1. And here is polydimethylsiloxane, non-constant viscosity. No psi1 given. Sometimes there's no psi1 given. It doesn't mean it's zero. It means they didn't measure it. So we tried to fix up our constitutive equation for this non-constant viscosity. This is the only constitutive equation we have. It has a parameter in the front. And I know from experience that it's confusing that the viscosity is both a parameter in this model and a material function back here. We do give them separate symbols, but sometimes we won't. There'll actually be constitutive equations later that will have this symbol in them. And this practice of putting material functions right in the constitutive equation, it's shorthand. We're going to see that that is, in fact, the prediction of the model in that given flow. And so in rheology, we've become casual about it, and we put the material function right into the constitutive equation. But the bottom line is that this is a parameter of the model, and it's only later that we determine that, oh, look, when you put steady shear flow kinematics on it, whatever is out in front of gamma dot turns out to be the prediction for viscosity. And then after that fact of noticing that, we say, well, then why don't we just call that parameter the viscosity? In other flows, there will be other material functions that will have this parameter in them. And those material functions won't be called viscosity. In fact, we saw that with startup of steady shearing. In startup of steady shearing, we imposed a step up in shear rate to the plateau gamma dot naught. This was our imposed shear rate, sigma dot, and then we measured and then we calculated what the response of a Newtonian fluid. And our calculation of what the shear stress would be for a Newtonian fluid was that it would step up immediately to a plateau with that parameter in it, that parameter mu. So here again, this parameter of the model is appearing, but it's not exactly the viscosity. Instead, it's the level of the eta plus material function. That eta plus material function turned out to be 0 for t less than 0, and it's equal to this plateau value for t greater than or equal to 0. This came from solving the constitutive equation, which has this parameter mu in it. So it's a little bit of a warning that the parameters of this mu is a parameter of the Newtonian constitutive equation, and later we're going to see constitutive equations with more complex parameters. And in fact, we invented a little quickie constitutive equation that would take into account shear thinning by putting a function in the front, which we then later determined was the prediction for the viscosity. We weren't so surprised about that, but nevertheless, this is a result of a calculation we did last time. If we choose for that function something that looks like the actual data, then we get a very reasonable prediction for viscosity, but we still get a nonsensical prediction for the first normal stress difference, because we always get 0 when all we do is multiply something times gamma dot. We always get zeros along the diagonal. And so I said we're going to need to do something more inventive to get a constitutive equation that will predict non-zero normal stresses. It's going to take us many weeks to get that inventive. Okay, we're not going to get that inventive for a while. So in order to figure out how to fix the constitutive equation, we need to look at material behavior under more conditions. So we went to the startup, which I've already discussed, where you start up the flow from rest and measure transient stresses. And when we predicted for the Newtonian case, we get this startup function that I mentioned before, which steps up to the plateau value, which is equal to that parameter mu. When we compare that with data, we find that the data do not step up instantaneously, and they do not step up to a level and just go to that level. They overshoot and then eventually come to a steady state. And of course, psi1 is not 0. We also looked at cessation of steady shearing, which is a very similar flow where you shear at times below 0 and then suddenly stop. And there are 3 transient stress quantities. And when we look at the prediction we looked at is also given in the book, but I believe we discussed it in our notes last time, is that it steps down instantaneously. But in this case, that's not what's observed. The stress does not step down instantaneously. Instead, it decays with some time constant. And there are first normal stress differences. If there is a first normal stress coefficient, then it probably doesn't decay instantly, and that's in fact what we see. It does not decay instantly. So we then went back and looked at our little fakey model that we were making, and I think I actually will I postpone doing it in detail, but the predictions are that it will predict the steady shear viscosity. It does predict in terms of the startup function, for instance. It does predict this level difference as a function of shear rate. I haven't shown that, but I'm going to show that later for a real model. It does predict a level difference, but it still continues to not predict this time dependence. And of course, any model proportional to gamma dot will not predict normal stress differences. So overall, attempting to fix up the model by just adjusting the viscosity and just knowing what the viscosity does as a function of shear rate, we can fix it up sufficiently to predict shear viscosity. But we can't predict the memory effects that are due to this startup and cessation business, and we can't predict the nonlinearities that are due to the normal stresses. So that's what we're still trying to get a handle on, is memory effects and nonlinearity effects. And going way back to the first slides I showed you in this class, those were two things I pointed out. In fact, going back to the movie that we saw, this bouncing was an elastic effect. The fact that when we turned this and it somehow came back was a memory effect. The fact that the ball, when it was sitting in a gravity field, would deform slowly is a memory effect. The fact that in draining two different burettes of different heights, the fact that twice the head gives twice the flow in the Newtonian case, and twice the head gives more than twice the flow in a shear thinning case, and less than twice the flow in a shear thickening case, is a nonlinear effect. And certainly, any of these normal stress effects are nonlinear effects. And we saw these in the movie. You can watch the movie again if you like on the web. The rod climbing you see in non-Newtonian fluids, and these normal stress effects that you see near the center of a spinning plate is clearly a nonlinear effect. So all those things we pointed out from the very beginning are still dogging us. We're still trying to find material functions that will tell us about memory and nonlinearities. So this was my summary last time. To proceed to better design constitutive equations, we need more material functions so that we know more about these nonlinearities and these memory effects. So the material functions we've discussed so far I can summarize with this plot. It's a plot that says what this shear rate function is and what the expected stress response, shear stress response is. And there's a middle column that I'm going to explain today, which is shear strain. Okay, so this is shear rate, shear strain, and shear stress. And so what we've seen in summary is steady strain in gives steady strain out. Step up in strain rate gives a step up in stress if it's a Newtonian fluid, and it gives a stress growth or a stress overshoot if it's a non-Newtonian fluid. I'll talk about strain later. And stress relaxation after steady shearing, a step down in shear rate, gives an instantaneous step down in the case of Newtonian fluids and a gradual stress relaxation in the case of non-Newtonian fluids. The next three sets of shear rate kinematics that I want to talk about are going to be related to this middle column, the strain. So I'm going to have to take a little detour and talk about strain. These are the next three that I'm going to talk about. I'm going to talk about creep flow, step strain, and small amplitude oscillatory shear. And in this flow, it's the center column of strains that is really key to understanding the deformation. Okay. So now, with every material function, we always start with that opening sheet that has kinematics on it, and then material functions. And we're going to do that now for the first one, shear creep. Okay? So shear creep, the kinematics look like this. Very different. In fact, I'm not really even going to be able to put up the true sheet, because in shear creep, it's not a flow where you define the shear rate. It's a flow where you define the shear stress. So I'll back up one slide and show you the typical early design for a shear creep experiment. And this is related to the one that was in the video where he used a falling weight to drive a torsional flow, a flow between between cup and bob. But this is a flow where we're doing a shear flow. So right here in green, there are two samples, each of which is experiencing this kind of a shearing flow where the one side is moving and the other side isn't. So on the bottom sample, it's the top that's moving, and on the top sample, it's the bottom. And what's being driven is, instead of this top plate being driven at a constant speed, it's being pulled at by gravity. Whatever the weight of this mass is, it's being pulled by a constant stress. This is called creep, and it was part of an early design because it's an obvious, easy way to put a constant deformation onto the sample, because gravity is whatever the force of gravity is in your room, that's what it is. It doesn't change with time. And so you don't need a complicated feedback loop to make sure that you get a constant velocity. You can just put a constant weight, and sure enough, this will give a constant stress. So it's a very easy experiment to do. And in a torsional flow, as I said, we saw in the movie a kind of a creep flow when he showed this concentric cylinders here, and he had a nice complex weight over here on the left-hand side that was pulling down, and then he was using it to torsionally drive this flow around in a circle. Okay, so we're going to see now a material function that looks like this Newtonian one that goes up like that, and this non-Newtonian displacement of the cylinder. This is going to be related to strain as opposed to strain rate. All right, so as I say on this slide, to explain creep, I'm going to have to explain strain. And to explain strain, which is deformation, I'm going to have to take a little bit of a detour here and start talking about strain. Now, strain, I think, is harder than both strain rate and stress. So this is going to come, I think, a little bit more difficult than some of the other things we've talked about. Strain is a measurement of deformation. What does deformation mean? Well, deformation means if I start out with some sort of a cube and I shear it, maybe it becomes a cube deformed like this. This is my old dimension. Now, deformation means change of shape. So in order to define the change of shape, we have to pick a method for following material particles from one place to the other. So the particle that was, say, in the center of this cube is now over here. It used to be maybe back there. The particle that was here in this corner is now up in this corner, etc. So that's why we get into the business of following particles around, because we're trying to define strain. And this is the mathematics on this slide, the mathematics of strain. If we postulate a coordinate system where we're going to keep track of where particles are, we can call R the location of a chosen particle P at time t reference. And then if there's some flow going on, that particle P will move to a new location at times t. And the strain will be related to the displacement function, which is the displacement function is the vector that connects the dots between a reference time and the location of the particle at time t. So it's this vector u. So if we have the vector r at time t ref, it's going to give the position of the particle, the x position, the y position, the z, or the x1, x2, x3 position of the particle at that time. And the vector r at t is the position of that, the x1 position, x2 position, x3 position of that particle at time t. So when we subtract these two vectors, we get the vector u, and so this is the displacement function u, is the difference between the location of the particle at time t and the location of the particle at time t ref. The shear strain is defined as the partial derivative of this function with respect to the x2 position. Now actually, strain is a tensor, and there's a more complicated definition of that when we get into tensor strains, but we're going to leave that off until week 12 or 11 in this class, because strain tensors are pretty complicated. So for now, we're just going to deal with shear strain because we're just going to deal with shear creep and two material functions that deal with shear strain. So to evaluate shear strain, we need to know the position of the particles at all times in a shear flow. And we can do that. Okay, we can do that because we know the velocity field in shear flow. So here's the velocity profile in shear flow, steady shear flow, for example. And we can relate this definition of strain to some geometrical change that's taking place in our particle. So if we have an initial square particle and deform it at some time later t, then this derivative du1 dx2 is related to the change in u1. Okay, u1 is the particle displacement function between the two times at this position versus at this position. Okay, so this derivative is saying what is the rate of change of the displacement function with respect to the distance x2. So the difference between this and this is indicated here by that difference. And the difference in the x2 positions between these two planes is just x2 here. So the strain, as defined here, the shear strain, is the inverse of the slope of the side of the deformed particle. So it's some measure of change in shape. Now, why the inverse of the slope? Why the slope? Why not 6 times the slope? Why not the slope squared? There's no one answer to that. There's no necessary shape, way of measuring shape. There's just ways we've picked. And this is the ways we've picked. We have to be consistent within those ways, but we're not actually required to do it in any one given way. So we can get specific about these displacement functions because, as I said again, we know the velocity field. For shear flow, and I'm starting with steady shear flow, we know the velocity field. V is equal to gamma dot naught x2, 0, 0. That means V1 is equal to gamma dot naught x2. So if I know where a particle is at time t ref, okay, if I know where it is in the its one coordinate, then its position at some later time t is where it started plus the velocity times the time. Right? It's just from physics, position is equal to initial location plus velocity times time. If you're 6 miles from Houghton and you travel at 3 miles an hour for 45 minutes, you can figure out how far you are from Houghton. Very simple equation. And so the velocity, we know the velocity. This is v1 here. So x1 at t ref, that's the initial position, plus x gamma dot naught x2 times t is equal to the position at any time t. And that's what I've written on this slide. The x1 position of the particle. So let's start with this vector. The initial position is just a given vector which has the reference initial state. The state at some later time in the one direction, the location, is the initial position plus the time difference times the velocity. In the x2 direction, nothing changes, right? All the particles in shear flow just move along at constant values of x2. All the particles move along at constant values of x2 and also at constant values of x3 because there's no velocity in the x2 or x3 directions. So at all times, the position of the particle in the 2 coordinate direction is just its initial position. The position of the particle in the 3 coordinate direction is just its initial position. So we go back to the definition of strain. The displacement function is what we need, and then we'll take a derivative of it. So we need to subtract the vector at time t, the location vector, minus the reference time location. Now we can do that. We just subtract these two vectors. And so we just subtract them term by term. This term minus that term is here. This term minus that term is 0. This term minus that term is 0. Okay, so once again, I'll point out to you that I'm letting the math and the definitions do the work. Once I think about the physics from the beginning, then I let the math do the work. Okay? And so I'm going to do that again. To calculate the shear strain, I need to take the partial derivative of mu1. This is the mu vector. This must be mu1. The partial derivative of that mu1 with respect to x2. So strain, shear strain, is defined, gamma 2,1 between time t ref and t is defined, triple equal, as the partial derivative of the one component of the displacement function with respect to the 2 direction. We've just derived that u1 equals t minus t ref times a constant, gamma dot naught, times x2. So what's the partial derivative of u1 with respect to x2?
Gamma dot naught.
Right. T minus T ref times gamma dot naught. These are held constant. This is a constant, but time is held constant. And we take the partial derivative, and because there's just an x2 there, it just becomes the coefficient in the front. So that is correct. If we talk about the strain between time t ref equals 0, then we get that this result is that the strain between time 0 and t is just the time times gamma dot naught. So this, let me sneak back to the previous grouping of slides. When I showed that summary sheet with the center column, this was strain. And here is that function we just derived. Time times gamma dot naught. It has a slope of gamma dot naught, and it's just equal to slope times time is equal to the line. So that's the strain we just derived. The strain for the stress growth is that there's no strain when the flow is not moving. And then again, we get time times gamma dot naught is the function for the strain. Or for the stress relaxation, again, when the flow is moving, the slope is gamma dot naught is the strain. And then when the flow is turned off, the strain is 0. So this is the function we just derived. So that works when the gamma dot naught, the shear rate, is a constant. But now we have to work a little bit harder to figure out how to calculate the strain when the shear rate is not constant. Okay? So let's talk about that. What about when the shear rate is not constant? Well, for starters, our definition of strain is sort of an instantaneous type deformation. It tells us that between some short interval, between 0 and t, or between t1 and t2, that we can calculate the strain as this product. How do we calculate it for a long time interval? And the answer is we can calculate it for a long time interval by taking our long time interval and breaking it up into lots of little short time intervals and adding them up. So that's what I'm doing here. I'm saying that the strain between two times that may be not very close together, let's say 0 and t are not close together, can be broken up into a whole bunch of little strains when they are close together. If we break it up into an even number of time elements, delta t, then I break it up into n of those. Break it up into n of those. Doesn't like my little circle, okay? Then this summation can just become n times the strain for each of the individual steps. And once again, we get that even if we have a large interval, which is what I showed on my previous slide, the strain is equal to the time times the rate as long as the rate is constant. If the rate is not constant, when we try to add these up, it's not going to factor out like this, but it's going to turn into, in fact, an integral. And that's what I'm showing here. For unsteady shear, for flows where gamma dot naught is not constant, then we have the same definition for shear strain, and we have the same result, which is that the instantaneous shear rate times the time interval is equal to the strain. As long as we have this short time interval, this still works. For long time interval, it just means that we have to add these up, once again, breaking up the time interval into short times. So for the time interval t1, t2, where that's a very long time interval, we can break it up into n short time intervals, which we then add up. So for the short time intervals, we have the quantity that goes in there. It's gamma dot 21, the instantaneous shear rate, times the short time interval. And then we add them up. But the problem is we can no longer say, oh, well, this is a constant, pull it out, we get n times delta t, we get t. That doesn't work anymore. But we can go back to calculus and say, oh, I know how to do a sum if I take the limit that this delta t becomes very, very small. So in the limit that delta t is small, this integral, this summation, this limit of a sum, this is the fundamental definition of an integral, is the limit of a sum. And so we're adding up these little baby steps to get the total amount of strain over the interval. So it's the integral of gamma dot over the limit sum interval dt. This is, in fact, the fundamental definition of an integral, going back to your calculus books. That may take a little bit of time to digest for you. The take-home story, though, is this last equation, which is that the strain is the integral of the rate between two times. And that fits with the calculation we did before for steady shearing, So for instance, for steady shearing, we can use this equation. Gamma 2,1 between two time intervals is equal to the integral from T1 to T2 of the strain rate between those time intervals. This prime in the integral just indicates that this time is a dummy variable of integration. And it's going to go away once I carry out the integration and evaluate between the limits. There will be no more t primes. T prime only exists inside this integral. Once I carry out the integral, it doesn't exist anymore. Let's try it for steady shear. For steady shear, the shear rate is constant. And so the strain between two times for steady shear is the integral of T1 to T2 of gamma dot naught dt prime. That's just a constant. So when we integrate it, we get gamma dot naught times T prime evaluated between T1 and T2, which is gamma dot naught T2 minus T1. Same thing we got before. The time interval times the shear rate is equal to the strain. So I got onto this discussion of shear strain because I was trying to explain to you some material functions in which the strain appears. So let's go back to that and see if I've explained that in such a way that these material functions now make sense. Let's go back to creep. Okay, what is creep? The last time I tried to show you the material function definition of creep, I left a lot of blanks here, and now all the blanks are filled in. Creep is a flow where there's no sigma dot here because I'm not actually going to specify the strain rate function. I'm instead going to specify that we impose a constant stress in a startup fashion. So at time t less than 0, the flow's not moving. Once it's time t equals 0, I apply a stress as if I put that weight on my sample. Now what's going to happen if I apply a constant stress to the sample is it's going to start to move. It's going to start to, in fact, creep along, which is why this is called creep. But it's not going to move at a constant rate. If it's a Newtonian fluid, actually it will, and we're going to derive that. But if it's a non-Newtonian fluid, it's going to take some time to get to steady state. And we saw that in the movie, in his creep experiment in the movie. If you remember this flow here. In this flow, when he started the flow, it went up like this. And during the flow, it didn't instantaneously come to a constant rate. There was this little startup region at the beginning when it wasn't moving quite at the same steady rate that it eventually attained. Okay? So the response to a creep experiment is a little bit complicated, and it has to do with the strain. Okay? The strain is the integral of the rate, and that's why we had to spend time defining it. The material functions in this flow are the strain divided by the stress. So it's like 1 over a modulus. It's called the shear creep compliance. And there's another one that I'm going to skip the slides for, which is called the recoverable creep compliance. And this is related in this experiment here. This is related to this amount that the flow reverses and goes backwards. I'm going to skip that. You can read up on that if you're interested. But that gets a little bit more complicated than I think we can digest at this point. But I do, yes?
The stress function that you specified there,
yes.
Does that in turn like specifies what the shear rate function is going to be, or?
The shear rate becomes something you calculate as a resultant.
Okay.
So you can't specify both the stress and the shear rate. That's over-specifying the problem. In the past, we've been specifying the shear rate, and then the stress turns out to be whatever the stress is.
Okay.
And then down here, we define the material functions in terms of the stress. Now we're going to specify the stress, and the shear rate is whatever it is. And in this example from the movie, the shear rate is the slope of this line, because this is, in fact, the strain. Okay? And so it is whatever it is. It's the measurable. So this experiment, he actually measured the strain because he measured the displacement of the device. And that's what's the measurable in the creep experiment. And that's why it's the strain that appears in the definition of the material function. Okay, so that's what's going on here. Let's get a little specific, because it's always good to have a specific example. Let's try to predict what this function would be for a Newtonian fluid. And it is a little tricky. So let me just say we are considering creep, shear creep, for a shear, and I'm going to ask the question, what is J of t? That's the material function for shear creep, called the creep compliance. For a Newtonian fluid. Now, when we made predictions for material functions using the Newtonian constitutive equation before, we always started with the constitutive equation. And that's still going to be the case. But it was easier when we specified the velocity, the shear rate, because that meant we knew the velocity directly. And everything just went, we just filled in the right-hand side of this equation. That gave us the left-hand side. And then we put those taus into the definition, and we were done. This time, the kinematics are that we know the shear stress. Tau 2,1 equals 0 for t less than 0, and it's equal to some constant value for t greater than or equal to 0. So now we've got information from the left-hand side, but we actually also have some information from the right-hand side, because the velocity field is still some unknown shear rate times x2, 0, 0. It's still shear flow. But it's not going to be that sigma dot, because that sigma dot is a function we specify, and as I just clarified from Juan's question, is we can't specify that. So there's going to be some function here, but I don't know what it is. Let me just call this, f for now, and leave it blank and hope that it sorts itself out. So we still have the stress constitutive equation. We know something about the stress as a function of time, and we know something about the velocity. We can take the velocity and plug it in. So let's at least do that. Del V plus del V transpose. So we need del V. If V is f of t, some function of time, x2, 0, 0, then del V is the same as it's always been, dv dx 9 times. And the derivatives go across the rows. And the velocities go down the columns. And this simplifies the same way as we've seen a bunch of times before. V2 is 0. V3 is 0. V1 is not a function of x1 or of x3. And dv1 dx2 is what? F of t. Right. So del v plus del v transpose must be 0. There's a f of t here, but then when I add to the transpose, there's an f of t here, and everything else is 0. So I can put this into the Newtonian constitutive equation. Tau equals minus mu gamma dot the tensor del v plus del v transpose. So tau must be equal to 0 minus mu f of t, 0 minus mu f of t, 0, 0, 0, 0, 0. And now, because we've gotten this far in analyzing our flow, we can go back to the definition of creep. For creep, the tau21 is given by this function. And because we now know what tau21 is equal to, we can back calculate what this f of t must be. Okay, this is what tau21 of t must be. So now I can back out what f is. I can see that tau21 of t must be equal to minus mu f of t. Therefore, f of t is equal to minus 1 over mu times tau21. So tau21 in creep is 0 for t less than 0 and tau naught for t greater than or equal to 0. So that must mean f of t must be 0 for t less than 0, right? And then minus tau naught over mu for t greater than or equal to 0. This f of t is clearly equal to gamma dot 2,1, the shear rate. It's the 2,1 component of the gamma dot tensor. So this is, in fact, the shear rate. We actually didn't want the shear rate, though, because we're going back here to the definition of the material functions, and we need the strain. But remember, we calculate the strain from the strain rate. It's the integral of the strain rate between the two limits that are given in the argument. So now that I've got the strain rate, I can integrate it to get the strain. So to calculate J of t, I need strain 2,1 between 0 and t. Strain 2,1 between 0 and t, by definition, so consider this a definition for us, is the integral from 0 to t of the strain rate over a dummy variable of integration. And the strain rate is this function with t prime plugged in wherever there's a t. 0 for t prime less than 0, and minus tau naught over mu for t prime greater than or equal to 0. Well, when t prime is less than 0 is irrelevant because I'm doing the integral from 0 to t, so that part doesn't even have any effect. So it's just this part. T greater than 0 is what has an part. So I just get to integrate minus tau naught over mu, which is a constant, integrated between 0 and t, dt prime. And so that's minus tau naught over mu t prime evaluated from 0 to t. And that's minus tau naught over mu t minus 0. We can use this result in the definition for j of t, and then we'll get our final answer that's shown on the next slide. I'll discuss this. I've run out of time, but I'll review this and discuss this the next time. But although this was a little tricky, the logic was very much the same as before. Starting with the kinematics, we impose it on the constitutive equation and put them into the definition. In this case, the definition required that we know the strain. And so we had to calculate the strain from the strain rate and get to this step, and we're just 1 or 2 steps from the end at this point. I'll finish that up on Monday. Yeah? You have a question?